Okay, in this question, I'm going to go through how to combine analytical techniques to deduce organic structures. And there's kind of like three main analytical techniques you need to know at AS level chemistry. The first is elemental analysis. The second is infrared spectrometry. And the third is mass spectrometry. Now, if we read the question that we've got in front of us, we're told that organic compound C is the following percentage composition by mass. So carbon has 54.5%, hydrogen has 9.1%, and oxygen has 36.4%. Now, this information here is what we get from elemental analysis. And we can use this information to determine the empirical formula of our compound. So first thing I would do is rewrite each of the percentages. So 54.5. H has 9.1, and then oxygen has 36.4, and then we divide each of these by the atom's molecular mass. So the carbon atom's mass from the periodic table is 12, hydrogen's mass from the periodic table is 1, and oxygen's mass is 16. So then we divide the percentages by these atomic masses. So 54.5 divided by 12 is 4.54. Hydrogen, which is 9.1%, divided by 1 is 9.1. And 36.4 divided by 16 is 2.275. So now we take the smallest of these and divide it by each of them. So the smallest is 2.275. So we'll divide that. So 2.275, 2.275, 2.275. So 4.54 divided by 2.275 is equal to 2. 9.1 divided by 2.275 is equal to 4. And 2.275 divided by 2.275 is, of course, 1. So this means our empirical formula for organic compound C is C2H4O. Now, remember, the empirical formula is the simplest ratio between the atoms in our compound. Now, the empirical formula is not always equal to the molecular formula, where the molecular formula is the actual ratio between the atoms in our compound. It can either be equal, the molecular formula can either be equal to this empirical formula, or it can be equal to some multiple of this empirical formula. So it could be, the molecular formula could be C2H4O, or it could be C4H8O2, or it could be even be C6H12O3. It could be any one of these or any other multiple of C2H4O. Remember, C2H4O is the simplest, but it doesn't necessarily mean it's the actual. And what we've got to do is use some of the other information we're given in this question to work out which one of these formulas is our molecular formula. Okay, so that's all we can do with the information that we're given by the elemental analysis. The next piece of data we're given is the infrared spectrum of compound C, and that is this top spectrum here. Now, the infrared spectrum generally has two parts. You've kind of got what we call the fingerprint region, which we can just cross out because this is due to background, and we do not need this information here. We are also given the region of interest, which is between, or is probably at a wave number more than 1,500. So our fingerprint region is kind of below a wave number of 1,500 centimeter to the -1, whereas our region of interest is usually above 1,500 centimeters to the -1. So what I would do is label the peaks now. So this one here is at 1,700 centimeters to -1, and it is sharp. So what I do is put in brackets S to say that it's sharp. Okay, because it has a small peak width. Now, this peak here is definitely broad, and I'd say it's roughly about 3,000 centimeters to the -1. And what we'll do, we'll put in brackets broad, or B. Okay. So now what we need to do is take this peak information and look for it within our data sheet that we're given for this past paper. Now, the data sheet is, so if we first look for the 3,000 centimeters to the -1, so we'll write it over here, 3,000 centimeters to the -1, we are given several options. It could be a CH alkyl group, alkene or arene, or it could be an OH in a carboxylic acid. Now, only one of these is broad, so the bond that we must be looking at with this 3,000 centimeters to the -1 must be an OH bond in a carboxylic acid. Okay, so that tells us that our compound must have a carboxylic acid functional group. So OH minus carboxylic acid. Now let's draw the functional group for carboxylic acid, and it looks like this: so R, C, O, double bond O, OH. So we know already that we have an OH bond. Now, we know in this compound, because it's got carboxylic acid in it, it must also have a C double bond O bond within it. Now, the other peak that we got from our infrared spectrum was 1,700 centimeters to the -1. And this could refer to, or this centimeter to the -1 is within this range here. So this must be the C double bond O within the carboxylic acid that we've not yet identified. So this 1,700 centimeters to -1 is a C double bond O within a carboxylic acid. Okay. So we know we must have a carboxylic acid functional group within our compound. Okay. Okay, the next thing we're going to do is we're going to look at the mass spectrum, which is the final piece of information here that we're given. Now, you can see there's lots of big peaks as well as lots of little peaks in this spectrum. So some of these peaks are due to isotopes. So we know that carbon usually exists as the isotope C12, but it can also exist as the isotope C13, which is one mass bigger than the carbon-12. So some of these littler ones are due to carbon existing as carbon-13, not as carbon-12. So really, the only peaks we need to use within this mass spectrum are the big ones. So let's label those. So we've got this one here, which we'll call peak 1. This one here, which we'll call peak 2. This one here, which we'll call peak 3. This one here, which we'll call peak 4. And this one here, which we'll call peak 5. Now, we're told down here that in this mass spectrum, a secondary carbocation is responsible for the peak with the greatest relative intensity. So that is this one, 3. So we know that this must be a secondary carbocation. Okay. Now, I think when looking at mass spectrum such as this, a little bit of knowledge about how mass spectrometry works really helps. So mass spectrometer is a machine which we enter our sample in, so our organic compound C, which in this case I'm just going to label as M. We enter it into a machine, and this machine really has two compartments. The first compartment breaks our compound into fragments. Okay, so what we get is it not only breaks into fragments but also ionizes the sample. Okay, so we get M without an electron, so M plus, as well as lots of fragments of that M. So we get F1 plus, F2 plus, and so on. Okay, so we get fragments of M, and not all of it gets fragmented. Some of that M actually stays as M, but an electron is lost. Some of our M is fragmented into different fragments, which we'll call F1, F2, and they also have a charge, a positive charge. Now, once they've been fragmented, once the sample has been fragmented, we enter it into a chamber, which has basically an electromagnetic field. Now, if we simplify how the machine works, we can basically say there is a thing at one end of the mass spectrum, mass spectrometry, which attracts the positively charged ions. And then there is, at the other end, there is something that repulses the ions. And this causes these ions to move. So at the end opposite to the first chamber, we generally have something that attracts positive ions, like a negative charge. And at the front end of the machine, where the ions enter, we have something that repulses these ions, causing them to move. So let's say like another positive, because remember, opposites attract, and things that are the same don't attract. So these positive charges are pushed through this machine, and it's basically like a race. So we have M plus racing against F1 and F2 plus. Now, M, which is the part of our sample that has kind of survived the fragmentation process, is going to be the heaviest because it's not been fragmented at all. So it's actually going to take a long time to move through this chamber. Whereas fragments 1 and 2 will be quicker than the M because they'll be lighter, because they've lost some of the atoms that M had. So depending on the size of F1 and F2, one of them is going to reach the end of the chamber first and hit the detector first. And this is an example of a time of flight mass spectrometer. So depending on how long it takes for these ions to move through this second chamber, depends on how big the ions are. So you can imagine, if we look at this graph here, the peaks at the very right-hand side, these are the slowest moving peaks. These are the heaviest peaks. And at the left-hand side here, these are our lightest peaks, or the fastest moving fragments through our machine. So this one here always refers to our M plus. So what the mass of the fragment or the molecule is before fragmentation. So in this case, the one here refers to our M plus. Okay. And we're told that the M plus has a mass of 88. So the M over Z basically refers to the mass of this ion. So M plus, we're told, has a mass of 88 grams per mole. Okay, and that's peak 1. Now, peak 2 is a fragment, and we'll call this F1. Okay, has a mass of 1, 2, 3, so 73 grams per mole. The peak 3 has a mass of 1, 2, 3, 43 grams per mole. Number 4 has a mass of 41 grams per mole. And peak 5 has a mass of 27 grams per mole. So the next thing I would do is, now let's look back at the possible options we had for our molecular formula of our compound C. We had C2H4O, C4H8O2, and C6H12O3. Now let's work out what the molar mass would be for each of these. So if we had C2H4O, the mass would be 44 grams per mole. So it can't be that one. That's too light because our actual M or our actual compound or compound C has 88 grams per mole. Okay, so let's have a look at the next one. So C4. So we've got 12 times 4 plus 8 plus 16 times 2, which is 88 grams per mole. So this must be the molecular form of our compound. So our compound must have this formula. So what I would do next, I would write down or draw some options for our compound. We know it's got a carboxylic acid functional group. Okay, and we know that carboxylic acid has 2 oxygens and hydrogen in it. So the rest of the compound must be a saturated hydrocarbon. Okay, so let's have a look at this. So we've got 1 atom of carbon, 2 atoms of oxygen and hydrogen in our carboxylic acid. So that leaves 3 carbon atoms left, 7 hydrogens left, and no oxygens left. And C3H7 generally refers to a carbon chain of 3. Okay. And it could be either this one. Okay. It could either be this one. I'll move this over here. It could either be this one attached to our carboxylic acid. So C, or it could be this one. So it could be C, 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 H, 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 and it could be this one. Okay, and actually in this past paper question, either of these compounds is an acceptable answer for our question here. Okay, so next thing I would do, just to make sure you get full marks in this paper, is identify what some of these fragments must be. Now, the fragments usually due to one bond being cut within our sample. So, for example, if we had a cut here, we would have this half of our compound as one fragment. So C plus, so carbon weighs 12 and 2 oxygens weigh 32 and hydrogen weighs 1. So that would be 12 plus 32 plus 1. So this side would weigh 45 grams per mole. And you can see actually in our spectrum, there is a peak at 45, which is about here, but it's quite small. And then we also have 3 carbons, which weigh 36 plus 7, which would be 43. 43 grams per mole. Now we're told that actually, so this would actually be a peak of 3 just here. Now we're told that this peak is actually due to a secondary carbocation. Now a secondary carbocation is something where a carbon, a positively charged carbon, is attached to it is itself attached to 2 carbons. Okay. Now the only way that we can get this is with this bottom compound here. Okay, because if this bond splits here, this carbon becomes positively charged. Whereas if the bond splits in this one, this carbon becomes positively charged. Now this carbon here is only bonded to one other carbon. So this would be an example of a primary carbocation. So actually in this mass spectrum, this half of the molecule is responsible for our secondary carbocation. And that's our 43 grams per mole bit. Okay, so this compound here must be our compound C. Okay. Now, I'm not going to identify some of the other peaks because I don't think you probably get any extra marks for that in the exam. But for your own purposes, you might want to try and identify some of these. So what I would do is start off with the original compound, which we know now is this bottom one here. And I would do little cuts in the compound to work out what some of these other fragments could be. So, for example, we could cut here. So that would get rid of 15 and we'd be left with 12 times 3, which is 36, plus 2 times 16, which would be 32, plus 1, 2, 3, 4, 5, which and 5. So this would be 36 plus 32 plus 5, which would be 73. So this would actually be peak 2 here. Now, this one that I've crossed out would be 15, and you can see there is a small peak at 15. Okay, just at this, after the fragmentation process, not much of this CH3 survives. It's mostly this that reaches the detector. Okay, so yeah, so what I've done, I've worked out 1, 2, and 3 for you, but you might want to then look at what other cuts we could do to this compound down here to find peaks 5 and 4. Okay, so yep, to answer our question then, our compound C is this compound in the bottom right-hand corner.